Assalamualaikum and a very good day I bid to Dr. Abdul Halim. I am Ezhar Kalani bin Jamain, Matrix ID of 25523, Petroleum Geoscience student. So today I'm going to present a topic of least square migration. So here's my presentation overview. Start off with introduction, problem statement and objective, which consists of some drawbacks of normal migration, main analysis such as significant gaps and current debates, and lastly, conclusion with recommendation. Migration is a process of decoding subsurface geological information from seismic data. This process is necessary to overcome the limitation of geophysical methods imposed by areas of complex geology such as fault, salt bodies, and also folding. Next, migration moves dipping reflectors to their true subsurface positions and collapse diffraction, resulting in a migrated image that typically has an increased spatial resolution and resolved areas of complex geology, which is much better than non-migrated images. Figure 1 shows the zero offset profile before the migration is applied. As you can see, the layers that are obviously horizontal are rising towards the center of the layer. This type of seismic profile does not actually represent an image of the Earth. These waveforms actually represent the impact of different background structures on the seismic source signals. This figure was taken from Lecture 7 Migration Principle slide. As you can observe, in the unmigrated section, the dipping events are not properly positioned. Also, the diffraction events are not collapsed and they are overlapping events in the unmigrated section. Meanwhile, dipping events in the migrated section is properly positioned and there is a collapsing of diffraction event in the migrated section. You can also observe there is no event crossing in migrated section. Next is the problem statement. Standard migration images can suffer from migration artifacts due to poor source-receiver sampling, weak amplitude caused by geometric spreading, attenuation, defocusing, poor resolution due to limited source-receiver aperture, and ringiness caused by a ringy source wavelet. To partly remedy these problems, least square migration (LSM), also known as linearized seismic inversion or migration deconvolution (MD), proposes to linearly invert seismic data for the reflectivity distribution. Furthermore is the objective. Firstly, to utilize the knowledge and understanding of least square migration method in delineating the complex structure in seismic data. Next, to evaluate the significant gaps between conventional migration method and advanced discovery of least square migration methods. And thirdly, to find out the current debates about the methods chosen for migration imaging. Moving on to main analysis. There are 4 things that I will elaborate. Firstly is the recent major advances and discoveries, then main people in this particular field, significant gaps, and also current debates. Recently, many researchers have discovered more advanced techniques in enhancing the image quality of the fault, fracture, and karst using the migration image. The new discoveries of advanced methods are least square migrations. Firstly, what is least square migration? It is an image enhancement tool and also a powerful data-driven approach to seismic imaging which aims to recover the Earth's true reflectivity by minimizing the misfit between the recorded seismic and forward model data sourced from CGG website. And it is also applicable to all seismic acquisition environments and geometrics, including land and ocean. The aim of this method is to update the reflectivity, improving illumination, and wave number content. The first step of LSM starts with a standard migration. Then after that, the migrated image will be used as a reflectivity model in Born modeling and create a synthetic data. After that, we will try to compare the differences between the observed data and synthetic data. If the differences are large and not within the acceptable threshold, then the differences will be migrated and used to update the image and form a new updated image. When the differences between observed and synthetic is acceptable, then it will form the final image. Moving on to the least square migration basic concept. It all started with the forward modeling where the data D computed by applying the acoustic forward modeling operator L to the velocity model M to get D is equal to Lm. But a better way to increase the visualization instead of that is by doing the transpose of the linearized forward modeling operator, which leads to the reverse time migration. For the RTM equation, the L transpose is applied to the observed seismic data. D gives the RTM image. Again, instead of computing an image at L transpose, we can get a better image with LSM. As you can see, the LSM formula, it is similar to the RTM formula, but with the addition of inverse Hessian. To solve this equation, we can't store and compute the inverse Hessian. What we do instead is pursuing the iterative solution by solving this optimization problem. We are trying to minimize with respect to reflectivity model M that the difference between predicted and observed data, predicted given by Lm, and observed data D. Next is the main people who are working in this field, which is Petroleum Geoservices, also known as PGS. PGS offers upgrade services in LSM and among the grad company that has an advanced technology in migration method, as well as helping the energy companies meet a wide range of geophysical objectives, from large-scale exploration for new resources or sites to more focused reservoir imaging challenges. Other than that, there are also many researchers have done their research study about this migration imaging, such as Dutta et al. With article entitled Making the Most Out of the Least Square Migration, and Liu et al. Entitled Least Square RTM with Ocean Bottom Knots, Potentials and Challenges. Based on their research, their main purpose is to mainly focus improving the detection of complex structures such as small-scale faults, salt domes, and other heterogeneous structures in seismic section. Next, for the significant gaps, it consists of conventional method and advanced method. For conventional is the reverse time migration RTM, and for the advanced method is the least square migration LSM. Next, we can clearly see that both of these methods has different formula. For RTM, it forms the subsurface image by reversing the forward wave propagation effects from the data. For LSM, there is an addition of inverse Hessian. Other than that, RTM is not as expensive as LSM and a simpler method, while LSM have better spatial resolution, more uniform illumination of the subsurface, and reduction of aliasing artifacts due to coarse source receiver sampling. Moreover, is the current debates. For RTM, older reverse time migration has proven remarkably accurate in a wide variety of image application, but it still has weaknesses such as RTM images often suffer from migration artifacts, uneven amplitudes, and limited resolution. While for LSM, most people agreed where LSM is better than RTM because of their enhancement. However, there are also few things that people still debate regarding this method, such as the quality of this LSM image is not better than standard image for velocity errors of 5% or more, and it is expensive and more complicated. Lastly, for recommendation, seismic migrationists in the last third of the 20th century devoted most of their efforts to improving the accuracy and reducing the cost of the migration operator LT. For the 21st century, their concentration is becoming refocused to develop more accurate and less expensive approximation to the Hessian inverse. This is largely driven by the exponential increase of both computing speed dollar and memory dollar, inexpensive GPU, and the need for more accurately identifying the geology of subsurface reservoirs. To conclude my presentation, LSM is important in the seismic wave imaging, and with the recommendation that has been suggested, LSM will continue to be one of the best methods in helping to produce a clear image which represents the geological structure below the surface. And here's two of my references for my technical review. That's all for my presentation today. I would like to thank Dr. Halim for taking his time to watch and evaluate this assessment. Assalamualaikum.